Alright, so in this video I'm going to be explaining another approach for domain adaptation, and it is a kind of adversarial because we have many approaches: adversarial, maximum mean discrepancy, and many other measures. And our task is predicting artificial titles and for abstractive title generation. So this article in 2019 that uses the idea of pointing the unknown words and uses this as a baseline domain adversarial training of neural networks, which I will explain in a different video. So it leverages these three articles, and it is in 2019. A common issue in training a deep learning abstractive summarization model is lack of large set of training summaries. Obtaining a good quality labeled data can be difficult and expensive, especially if author-generated summaries are desired. One option is to train on data from another domain with author-generated titles. But because of differences between domains, the performance may be less than adequate. These differences include different vocabularies, different grammatical styles, and different ways of expressing similar concepts. This paper examines techniques for adapting from a labeled source domain to an unlabeled target domain in the context of an encoder-decoder model for text generation. In addition to adversarial domain adaptation, we introduced the use of artificial titles and sequential training to capture the grammatical style of the unlabeled target domain. Evaluation on adapting to or from news articles in Stack Exchange posts. These are very different kinds of domains. The way people write things are completely different. The grammar, everything. So it indicates that the use of these techniques can boost performance for both unsupervised adaptation as well as fine-tuning with limited target data. Of course, this one is more interesting and more challenging. So there are three contributions proposing the use of artificial titles for unlabeled target documents to train a decoder to learn the grammatical style of titles in the new domain. Proposing to train the decoder in a sequence of steps that encourages the source and target embedding spaces to remain aligned during adaptation. Showing that our model improves performance over ADA and an expanded vocabulary alone, and further that a limited amount of labeled target data can achieve performance close to training on all labeled target data. So this is encoder-decoder RNN for text generation with a classifier for adversarial domain adaptation of the encoded representations to an unlabeled target domain. For example, we say that your article is domain D, and we have a domain classifier for that. But the task is just summarization, title summarization. So we use this adversarial idea 2016, and we use encoder-decoder RNN with domain adaptation. So here is just encoder-decoder. So the domain classifier has two dense 100-unit hidden layer followed by a softmax. The concept representation vector, this is a concept representation vector. It is computed as the bidirectional LSTM encoder's final forward and backward hidden state concatenated into a single state. During training, the gradient from the domain classifier, this gradient is reversed to be negative before being propagated back through the encoder, encouraging the embedded representations to align by adjusting the feature distributions to maximize the loss of the domain classifier. In contrast to the classification losses used by Gannon for training the model, we use the generated sequence loss together. So it depends on your task. You should always involve your task into this, the loss of your task. It could be classification, but here you see it's a generated sequence. And the decoder loss is just negative likelihood of the target words at position T. So this one is minus log of P. And the domain classifier loss, so this is the domain classifier loss, is the cross entropy between predicted and true domain labels. Because before, in pre-processing, we've already defined our domains. Even if we don't have data sets for different domains, we can use techniques of clustering for domain discovery, which is another issue. So we followed the schedule from Gannon for adjusting lambda for the encoder. By the way, this is just single source adaptation. Sometimes you have multi-source. But multi-source adaptation, domain adaptation, is a little bit different from domain generalization. They look completely the same because even domain generalization has a multi-source. But in the domain generalization, you never have access to test data for training. And you have many limitations. And there is no intersection with the probability distributions of the source domain. The target domain source domain completely isolated. There is nothing common. So when you sample from source domain, there is nothing that you can sample from target domains. There is no intersection. So here we have this flow chart. We pre-train on artificial target, then we pre-train on artificial target with adaptation to source. Then we train on source with adaptation to artificial. Do you think your brain does these things? Do you really think that your brain is like this? Doing everything repeated several times? I don't think so. I think the design of brain is much more beautiful. It's like a microservice architecture, different components. It's a separation of concerns. So in artificial titles, the style of the unlabeled target may be different from the source. Stack Exchange is more casual and includes more slang than news articles. To capture the style of unlabeled target, artificial titles were synthesized. So our adaptation method, this model, AZADA, is shown, and a model with joint vocabulary is first pre-trained on artificial titles for unlabeled target domain. The embedding space of pre-trained model is then adapted to the source domain to continue training on the target domain with the source domain as the auxiliary. With the joint embedding space defined, the model is trained on the source domain, which has title. So the data set has a stack exchange. If you go from this source to this target, you see a big domain shift. And for experiments, they use this pointer generator model because it's a baseline. And then you go from source domain to target domain, this direction. But here you see that the other direction. You go from stack to news. And you have some measures, this measure that I've explained several times. So this is the histogram of news and stack exchange vocabularies showing the number of target domain joint vocabulary or tokens that are underrepresented in source training data.